Okay, welcome to Compass. Today we have Rodrigo Duran. He did the PhD in Oregon State with Russell Summerson, right? Maybe 5 years ago, something like that.
Finished 5 years ago.
Okay. He's an independent scientist working, I think before was SPACE, now is Planetary Research Institute, or Planetary Science Institute.
Yes.
Okay. But he's based here in South Florida, right?
South Florida, yes.
Okay. Welcome and thank you.
Thank you. Thank you, Josefina. Thank you, everybody. So, today the talk is on the physical mechanisms controlling loop current eddy separations and the seasonality that comes from those mechanisms. This is work in collaboration with Nick Aksami in Norway, San Liang, currently in China, used to be in the US some years ago, and Christian Appendini, who is in Mexico. And let's see. All right, so you already all know this, but we've got to start somewhere. So loop current is a very energetic western boundary current entering the Gulf of Mexico through the Yucatan, next to the Yucatan Peninsula, the Yucatan Current right here. And it has two main states. It's retracted, state number 1, or it's extended, state number 2. And when it goes from 2 to 1, it usually sheds a big loop current eddy that, between the loop current and these eddies, there's a number of very important impacts. Like, for example, tropical cyclones tend to rapidly intensify because of the very warm water. The vertical structure is about 500 meters, 1 kilometer deep, so it doesn't matter how much the hurricane will mix, it still will have fuel. And it also impacts offshore safety, marine ecosystems, a number of things. To quote the National Academy of Science, hurricane intensity, offshore safety, harmful algal blooms, oil spill response, the entire Gulf food chain are all affected by the position, strength, and structure of the loop current and associated eddies. So, and just to give a little bit of context, the National Academy of Science in 2022 started a 10-year project. They assigned $125 million to a number of projects studying the loop current. They want to understand, specifically the shedding of loop current eddies is a major topic they're interested in. And but to give some context, Chevron has built the Bigfoot deepwater platform. So all the northern Gulf of Mexico is full of oil platforms, offshore structures. And this is the deepest platform ever built, at least it was at that time, with a cost of $4 billion US. And there was a problem with the tendons that anchor the platform to the bottom. Now these anchors need to be purpose-built for the Gulf of Mexico because of ocean currents deep ocean currents that are related to the loop current and the eddies. And they're especially problematic when they coincide, these strong currents coincide with a hurricane. So these anchors failed, and there was a 2-year delay that cost them an additional $1 billion US. So to put that into context, these $125 million that the National Academy of Science dedicated for 10 years of studies is about 3% of this $4 billion that so I would hope that it makes a point that we need to invest in science and business will benefit. All right, so let me start with what I will claim we already know, but I'm also interested in hearing differing opinions. I'm sure there's different opinions out there as well. The first thing is that in August and summer, there's a 2 to 3 times higher probability of an eddy shedding event. The loop current is 2 to 3 times more likely to shed a loop current eddy in August or September. And also in December, there's almost no eddy separations. So the Hall and Levin in 2016 studied this in depth, and they found what I just mentioned, 2 to 3 times higher probability in August, September relative to the uniform probability of 0.1 eddies per month. And they almost zero December, maybe zero, I'm not sure, shades. Likewise, this is Hamilton 2014. This is a technical report with several experts in the loop current, and they found the same. They analyzed a number of data sets. They came to the same conclusion. Chang 08 in 2012, nearly half of the events in the summer out of 37 years of data. Lino Tichati et al. 2014, enhanced August-September probability. December is rare, 17 years of data. Algal, half events in July, September, 13 years. Vukovic, 2007, 0 separations in December out of 32 years of data. So what is the mechanisms controlling this seasonality? This is a figure from Holland Levin, and here you can see the uniform probability, about 0.1 eddies per month. The fraction here, the fraction here is the confidence. So the lower this number, the higher the confidence, and in red are the significant values that this is actually a trend. This is actually a signal that we're seeing here, and you can see that August, September have roughly 3 times as many separations as the average, and then December there's either 0 or 1, I'm not sure. And models also see this kind of trend. So this is the model that I'll be analyzing, or that I'll be showing results from. If we look at the monthly histogram of separation events, in September we have twice as many as any other month, but there's no separations in December. And in blue is the histogram by seasons. Now, an important date that we'll come back to is August 23. Hal and Levin did a number of tests, and one of the things they found is there's a season within which eddy-shedding events are more likely, and the center of that season is August 23rd, so we'll come back to that date. All right, second thing that I would like to claim that is known is that loop current frontal eddies drive separation and are a very important part of the loop current eddy separation process. Some of the first people to report that were before altimetry, Vukovic and Moll in 1985, Fantantoni in 1998, Savali, this might be one of the first altimetry studies. Schmitz did an in-depth review of all the data at that time. He found 2 separation modes, and they're both involving loop current frontal eddies. And so these loop current frontal eddies are cyclonic eddies. They're smaller than the loop current eddies, and we'll talk about them in some detail. So for the separation to be permanent, Schmitz mentions the cyclones must slip in behind the separated loop current eddy. OA presents numerical results showing how this mechanism can work. Also, they find it's related to barotropic instability, and I'll mention what I mean by that in a minute. I'm not going to be able to pronounce that, but they in 2013 found that they used joint sensitivity. So this is an inverse problem. They're asking, this is what we're interested in. They're asking how can we get it, and they found that loop current frontal eddies induce shedding as a mechanism that related to the separation. Probably going to pronounce this incorrectly as well. The Hanaf until 2014 surface observations confirmed the mechanism by OA, the numerical study. So these 2 studies, Donahue and Schindler et al. 2016, they used very well-populated arrays, 3-dimensional arrays to measure, and they were there for a number of years. They measured 2 to 3, something like that, 3 detachments and 4 detachments, I think. And what they found is they confirmed what OA had seen and other observations had seen. There's cyclonic perturbations that travel along the boundary, the front of the loop current, and they get intensified through barotropic instability as they're traveling. And then these cyclones are related to the cutting of the loop current and the shedding of an eddy.
Is there a preference as to which side of the Yucatan Strait those are?
We'll get to that in some detail. So anyway, another modeling study. Now this one, Yang et al. And this Yang et al. These are 2 different Yang. In 2020 and 2023, they find that these cyclonic perturbations are first formed by barotropic instability and then intensified by barotropic instability, and that they are definitely an important part of the separation. They use self-organizing maps. They find the same thing, the current frontal eddies. And then a very recent study that hasn't even been published yet, they used 29 years of observations. They find that every single loop current separation involves loop current frontal eddies, and that loop current frontal eddies are essential for the separation to be permanent. All right. But what controls when this happens, and how exactly is permanence established? That's what we hope to answer. So there's no mechanistic explanation for decades of seasonal observations. our hypothesis is that Yucatan Current seasonal cycle drives loop current frontal eddy formation, modulates the shedding probability and the separation permanence. And the way we got to this is by connecting the upstream forcing to the separation seasonality using physics. And the key here was reframing everything in terms of energy transfers. The data we'll use is 30 years of altimetry, the best possible combination of satellites produced by the French CNES. Then a 22-year reanalysis by HICOM at the Gulf of Mexico is roughly 9-kilometer resolution. This is the US Navy operational model. Then we're going to be using energy transfers from mean kinetic to eddy kinetic energy, and also the eddy wind transfer of eddy energy into the ocean or out of the ocean, also known as eddy killing when it's taking energy from the ocean. We will use information flow, which is a rigorous way of detecting causality. So in the 1940s, something like that, Shannon was working at Bell Labs. They wanted to understand how information can be sent from one place to the other. They were dealing with phones, no internet at that time. But Shannon did develop a mathematical theory that's been incredibly productive, and it's called information flow. And San Liang, one of the co-authors of this study, he developed a way to estimate the information that is transferred from one time series to another time series. If there's a transfer of information, then there's a causal relation. So we do that as a confirmation of the energy transfers. And then finally we use transport barriers. Sure, everybody here, or maybe most here, have heard about transport barriers because Javier and Josefina, your very own, are worldwide experts on that topic. These transport barriers are active transport barriers, so these are the barriers to vorticity. So vorticity determines the evolution of the fluid. That's why it's an active transport barrier. And we will talk about vorticity transport barriers as well. All right, so this is the spatial picture. On the left of each panel, we have the 22-year time mean of the HICOM reanalysis or the 30-year time mean of the altimetry data. Same color bar, even though the resolutions are not directly comparable. So this is mean kinetic energy. You can see that the Yucatan Current has produces a maximum mean kinetic energy right where it interacts with the Yucatan Peninsula, right here. Same in, so in each panel you'll see that the model and altimetry correspond very closely, and which maybe is not surprising since this is an operational model simulating all available information. And so that's mean kinetic energy. Then vorticity here, normalized by local planetary vorticity. You can see it about, even though this is a 9-kilometer model, it reaches right about it's comparable to local planetary vorticity. So this is extremely intense vorticity production that we see here. And so this is cyclonic, anticyclonic. The loop current is anticyclonic vorticity. The Yucatan Current to the west of it is anticyclonic. And now this is gamma. This is the transfer between mean kinetic energy and eddy kinetic energy, as published by Lian, also same co-author of this study. Now this formulation of the transfer between mean kinetic energy and mean and eddy kinetic energies has a few advantages. One, it's derived from first principles from the primitive equation, so there's no quasi-dystrophic assumptions here. Number two, it's done in a way that is not typical for oceanographers. This was actually, he did his PhD in applied math at Harvard on this topic in 2002, but he published this in 2016. He's been working on that since then. And the benefit of the method he developed is that it is replicable. So once you define which are the energy windows you want, so for example, we're interested in seasonal to intra-seasonal, then there's only one energy transfer that can arise from that. As opposed to all other formalisms where, depending on how you manipulate the nonlinear terms, you can even get negative energy, and you can get different results, even though the windows are the same. So, I'm not an expert on this, but I know This has advantages to other. And another thing is that just because there's a transfer of energy, there's no loss of energy. So energy is conserved in the system. Now this is all needed because this is a point-wise computation. The transfer of information comes from 1955 by Lawrence. He was looking at the cycle of energy in the ocean and atmospheres, but that was developed in an spatially integrated formalism. And going from spatially integrated to local is not a trivial question, and this is a correct way of doing it.
Quick question.
Yes.
Often the mean kinetic energy is defined as a low-pass version of the velocity. Yes. Is that the case here, or is it just a mean?
Yes, it's a 90-day running mean, and we did some tests, and we can talk about that. I'll probably talk about that a little bit more. Yeah. That's right. And so the spatial story is that the Yucatan Current, as it interacts with the Yucatan Peninsula, it creates this energy cascade that promotes loop current frontal eddy formation. You'll note that the most intense eddy kinetic energy is on the other side of the loop current, and we'll also get to that. Although there is a peak right here where all the action is happening in the rest of the fields, but this is where eddies do their thing for the most part. All right, so this is the temporal picture now. This is from the reanalysis. Now, each one of these bands here is a separation event in the model. I can't compare observed separations with model quantities. I need to compare model separations, loop current eddy separations with model quantities. So these are separations in the model, and on the top we have the mean kinetic energy. Now, you might note there is a yellow and orange periodic approximation to this time series. The yellow one is the closest fit to the data that has a 365 period. So I tell the data, I need a fit to the data, a harmonic fit with a 365-day period. And that's what I get. The orange one is use singular spectrum analysis, and that's, you could say, an objective way of getting the harmonic signal in there, because I do not give it any information. I just tell it, give me the most important harmonic in this data, and it returned a 365-day harmonic. I just put both of them in there so you can compare them. Now, singular spectrum analysis can have a time-varying amplitude. It can also have a time-varying period, and that's why you see that the amplitude doesn't always match exactly, but the period is pretty exactly 365 days. These black lines, dotted dashed lines here, is August 23, which you might remember is the center of the season where loop current eddies separate more often. And what we see is that mean kinetic energy peaks right before this date every single year, right about. All right. Now, this here is the transfer from mean to eddy kinetic energy, and it has the same time dependence with 365-day peaking period, which is peaking right before the main date or the center of the season for loop current eddy separations. This here is vorticity in blue with the same two fits to that data, and also the 90-day running mean in black. And once again, we see the same pattern. Now, eddy kinetic energy is messier, as one might expect. It is turbulent. But the important thing here is that 96% of separations coincide with a vorticity peak, and 73% of separations coincide with a peak in transfer from mean to eddy kinetic energy. This is the same figure, but now from 30 years of altimetry with observed separations in the bars here. And we get similar statistics. 85% of separations coincide with vorticity peaks, 78% coincide with energy transfer peaks. And so I don't know what's the base rate of coincidence for this coincidence, but I can ask, what is the biggest coincidence rate or base rate that I could have, and while these results are still significant? And what we find is that with 99.9 confidence, even if 60% of these coincidences were random, we would still have a significant relation between vorticity and separations. And we also note the converse of that. So for example, here, mean kinetic energy is low in this period, and you'll notice this is a period where separation ceased to happen for a little longer than typically, and both the mean kinetic energy, the vorticity, or the transfer of mean kinetic energy to eddy kinetic energy and vorticity tend to be in depressed states. And that holds also for other periods. All right, this is the same thing I just mentioned, so I'll skip that. So this is the causal chain that we've shown here. It's in the summer Yucatan Current intensifies. Right about June, July, there's enhanced mean kinetic energy production next to the Yucatan Peninsula. The transfer from mean to eddy kinetic energy peaks in a bit later, around the same time or a little later. This promotes loop current formation, loop current frontal eddy formation and growth. Cyclonic eddies are either formed or energized. And finally, this continuous production of vorticity over the summer produces and feeds and preserves a vorticity barrier that ensures that the separation between the loop current and the loop current eddy is final. All right, so let's see how this works. This is a movie of one separation event in 1994. The time series up here is the same time series we already discussed in the model, but only in 1994. Mean kinetic energy in blue. This here is gamma, the transfer from mean to eddy kinetic energy. This is eddy kinetic energy, and this is vorticity. This line here will give us the date. As the movie plays, the date will move forward, and this line will continuously show what date we're at. In the top left here, we have sea surface height. In white, black, we have the loop current, as seen from the 17 centimeter sea surface height contour. The black contour here is the minus 28 or something like that sea surface contour. So we will use that to identify loop current frontal eddies. Now, here in Miami, you also have experts on on eddy identifications. As it turns out, defining an eddy is a highly non-trivial question, and therefore identifying eddies is a highly non-trivial matter as well. Javier and Josefina are experts, I'm sure you've heard about that before, but for our purposes, any cyclonic perturbation, that's what we're interested in. Doesn't matter whether there's water crossing through the boundaries or not, and because the minus 28 centimeter contour, sea surface height contour is very convenient, I will use that to pinpoint loop current frontal eddies. Now, whether these are truly eddies or not, that's a different question. I didn't even bother with that for this study. In the middle panel here, we have relative vorticity, again normalized by planetary vorticity, and with the same sea surface height contours in white and black that we just talked about for reference. This here on the top right is the active finite time Lyapunov exponent. So ridges of this quantity will indicate transport barriers of the vorticity field. And as you might have heard, transport barriers of just trajectories, passive tracers in the ocean velocity field, what these barriers will do is they will normally attract nearby trajectories and then cause them to elongate along the barrier, with the important caveat that the trajectories cannot cross this barrier. That's why they're a barrier. So they attract nearby trajectories, but they cannot cross this barrier. And the way vorticity barriers work is exactly the same. The math is very different because this is an active field, but the concept is the same. So it will attract vorticity normally to these barriers, and then vorticity will tend to travel along these barriers, with important caveat that vorticity cannot cross these vorticity transport barriers. And these barriers are signaled by ridges of this field, like this here in black and red, sorry. Same sea surface height contours for reference, as we've discussed. And here at the bottom, again, the sea surface height contours are the same in white and black. On the left, we have mean kinetic energy. In the middle, we have the transfer from mean to eddy. So positive is from mean to eddy, and blue is from eddy to mean. And then on the bottom right, we have eddy kinetic energy. Notice the scales here. This is about an order of magnitude larger than the eddy kinetic energy. All right. So I'll now play a movie. The first thing we're going to see is we're going to see a false separation. So there's going to be the sea surface height contour is going to break. but the vorticity is going to be connected. And I'll stop at that point to make a few remarks. Alright, let's try this again. There. So if we were to ask whether the loop current eddy has separated from the loop current and answer that looking at sea surface height contours, we would say yes, the eddy has separated, right? You can clearly see that right here. But if we look at vorticity, we can see that the anticyclonic vorticity of the loop current remains connected to the anticyclonic vorticity of the loop current eddy. And if you look at the barriers, it's difficult to tell here, but just follow the blue here. If you follow the blue, let's see. Let me go back a little bit. All right. Like here. You can see the connection in relative vorticity between the loop current and the loop current eddy that is about to separate. And if it's clear enough, I'm not sure if you can see it here on the projector, but if you follow negative vorticity along this barrier, you'll see that negative vorticity is connected along the barrier with negative vorticity. And here it's very clear, and here, this path you see here is this path you see in the barrier. Meantime, and you'll notice that we're reaching the peak everything, right? Everything's about to peak. And right around the end of August, beginning of September. Now, this loop current frontal eddy, you can see is being intensified by the mean kinetic energy just to the east of it. You can see the transfer here of energy as it's spinning this eddy cyclonically. And what we're going to see next is that the sea surface height connects again, but then this eddy that's here will move between the loop current eddy and the loop current, and this barrier, instead of connecting blue with blue, will now separate blue from blue. A different barrier will form, separating blue from blue. And that barrier is going to isolate the eddy. There's going to be a barrier up here, and there's going to be a barrier down here isolating the loop current. So there it is. Now they're separated, the barriers are moving, and this eddy is still being spun by the mean kinetic energy, still being energized. And you can see now this is just the beginning of the break. This is the beginning of the period where anticyclonic vorticity is separated from anticyclonic vorticity. And that will continue and stabilize. So, for example, here, at this point, there is anticyclonic vorticity from the eddy that could potentially reach the loop current. But this intense cyclonic vorticity is also forming a transport barrier that will not allow this vorticity to connect with this vorticity. Soon enough, when I hit play again, another barrier is going to form here. So this pool of anticyclonic vorticity will now be dynamically isolated from the loop current eddy and from the loop current by two barriers, one here and one here. And at that point, the separation is permanent. The loop current eddy and the loop current cannot connect again. So this is the false separation here. You'll notice the barrier goes from blue to blue right here, and eventually the blue and the blue are completely connected. This barrier here is actually connecting the loop current with the loop current eddy. So their vorticities are connected. It's separating them, that's connecting them. Nonetheless, you do have the beginning of a loop current frontal eddy that is being intensified and spun by the mean kinetic energy, and that soon will do its thing. This is when the true separation happens. The separation is about to happen here, and you can see the vorticities are connected, but then maybe a week later, the vorticities are now disconnected. And importantly, the production, the interaction with the Yucatan Current is continuously production. The interaction of the Yucatan Current with the Yucatan Peninsula is continuously producing cyclonic vorticity. This is what preserves and maintains that vorticity barrier, so that regardless of what turbulent whatever is maybe going on, the anticyclonic vorticity of the loop current eddy and the loop current cannot reconnect. There's a continuous vorticity production that produces a barrier. This is a different example. The previous example is the case where the loop current frontal eddy moves in from the west towards the east. And in this case, in 1996, we're going to see loop current frontal eddy moving from the west into the east, which is actually the more common case. And that's why we were seeing most of the eddy kinetic energy
all the way
happening.
around.
Yes, yes. So vorticity is still produced where you would expect, but then this cyclonic vorticity travels all the way around. And actually, while it's traveling, there's at least 3 different mechanisms that have been published that intensify these loop current frontal eddies, and observed, by the way, not only so loop current frontal eddies have been observed and hypothesized to intensify as they're moving along the front. Once they're here, they will cut in through from the east.
Are they intensifying because they're being vertically stretched?
That's one of the mechanisms, and then there's baroclinic instability, and then there's nonlinear interactions between the loop current and the loop current frontal eddy. So those are the 3 mechanisms. So all the rest is quite similar, except you'll notice that mean kinetic energy peaks here a little before these, and we'll see the permanent separation right around here. And the reason they don't exactly coincide is because the Yucatan Current needs to line up and right in the right direction for this vorticity transport barrier to be in the right angle, in the right direction, to keep the loop current and the loop current eddy separated. So let's play the movie here. I won't interrupt as much. Here's the frontal eddy that's being formed, now breaking in from the east. Vorticity barriers are about to intensify, and now you'll notice this is what I meant. You need the Yucatan Current to align in the right direction. So now you can see it'll spin this eddy. The direction of the barrier, which is right here, is just as it needs to be to keep the anticyclonic vorticities separated. And there's a loop current frontal eddy right in the middle, being part of that barrier.
Very cool.
Alright. So this is right before the separation. You can see vorticities are still connected, the anticyclonic vorticity is still connected. And this is after the separation. You can see a very intense barrier related to the production of cyclonic vorticity, related to the Yucatan Current, and you can see the Yucatan Current spinning this eddy and this cyclonic perturbation that will cause this separation to be permanent. Right, and to finish, now we said this is as far as the summer, fall. Why are loop current eddy separations more common? Let's revisit the question of why loop current eddy separations are very uncommon in December. It's a combination of 3 things. Number 1 is geometric. We already said that most likely the loop current eddies separated in the summer fall. So by the time you reach the winter, the loop current will be in a retracted state. You need the loop current to be in an extended state to be able to have a loop current eddy separation. So that's the first thing. The second ingredient to the recipe is that the Yucatan Current mean kinetic energy is in its minimum, its annual minimum. That means the production of vorticity and the transfer from mean kinetic energy to eddy kinetic energy is also at its minimum. So there's less likelihood of loop current frontal eddies being produced and or intensified. And then the third ingredient is eddy killing. This here is the 22-year time mean. So this is the energy, the eddy energy of the atmosphere, the transfer between eddy energy in the atmosphere and the eddy energy in the ocean. So if you see blue, negative, that means the eddy energy in the atmosphere is extracting eddy energy from the ocean. And where does that extraction happen? The most intense energy extraction, eddy killing, also known as eddy killing, happens right in the area where the east loop current frontal eddies cut through the loop current. And as I mentioned, this is the more common mode of loop current frontal eddies causing loop current eddy separations. So if there was a loop current frontal eddy, which is unlikely to happen, and if the loop current was in an extended state, which is unlikely to happen, then eddy killing would come in and extract energy from the loop current frontal eddy, making it lose its importance, its relevance in this particular topic. And you can see here the time series. So this is the 22-year time mean to see the spatial pattern. And but if you look at the time series, these black lines, these dashed black lines now are December 15th, just to signal where December is every year. And you'll notice that eddy killing becomes extremely intense in many of these Decembers. So it's very, and this is also being observed in other western boundary currents. It's not particular to the loop current. Eddy killing becomes pretty intense in west boundary currents in the winter. All right, so maybe to leave some time for questions. We believe we've solved a long-standing mystery with a mechanistic explanation. We've established causality. I didn't speak too much about causality, but again, we have all these time series and we can estimate the transfer of information from one time series to the other. So that way, if for whatever reason you didn't believe in the energy, the physical mechanisms of energy transfer, we still have the transfer of information showing there's a causal relation between the mean kinetic energy causing the vorticity and the mean kinetic energy causing eddy kinetic energy. Also, we have a causal relation between mean kinetic energy and gamma, the transfer from mean to eddy kinetic energy. So we can detect a transfer of information from mean kinetic energy to all these other time series, and that's how we can establish causality in this particular sense. Do you have a question?
Yeah, the date you chose for the peak is kind of close to when the peak of the hurricane season is.
That's a good point, yeah.
Yeah, it would be surprising if there weren't a connection between those two.
I'll mention a few words on that in a minute. And to the best of my knowledge, this is the first time that active transport barriers have been used in an oceanographic setting to show a mechanistic explanation for a phenomenon. And so that with those ingredients, we have a unifying framework that can be used to predict, hopefully, that's future research of course, but hopefully we can predict or advance at least our predictive capabilities of loop current eddy separation events all the way from the upstream forcing to the local dynamics. So we used those tools there. So yes, as you just mentioned, the Mississippi Delta is one of the locations that is most hit by major hurricanes, so category 4 and 5 hurricanes. And the reason for that is because as hurricanes move towards the Mississippi Delta region, they rapidly intensify with the fuel being either the loop current or the loop current eddies. As I mentioned, they have a very deep vertical structure, so the hurricane can mix as much as it wants, it's still going to be able to extract energy from that current. So there's one very important. There's billions of US dollars lost whenever this happens. So that's a very important application right there. Even when there's no hurricane, still offshore operations sometimes have to stop for months at a time just because these currents are so intense, and they can't do anything. So that's a lot of money lost. So if they can they spend a lot of money trying to forecast these kind of things. So this is definitely relevant for them as well. And there's fisheries, there's tourism, there's pretty much everything in the Gulf of Mexico depends on the loop current and the loop current eddy separations. But there's also broader applications to western boundary currents, climate mesoscale interactions, and perhaps even a prediction framework for oceanographic processes. So key takeaways. The Yucatan Current seasonality drives separation timing through energy cascade. All separations require loop current frontal eddies, or at least cyclonic vorticity. The mechanism has been confirmed. Vorticity transfer barriers determine the permanence through dynamic isolation. And in the winter, there's a triple suppression, including eddy killing, that explains why it's extremely rare to find any loop current separations in December. And we have now a physics-based explanation. We have some predictive capability. And there is now a bridge between the large-scale forcing and the local response. So I'll leave it at that, and I'm happy to take any questions or comments.
Okay, thank you very much. Questions? Brian, I will come with the microphone.
Hi, that's very nice, and the seasonal cycle is always fun because you got many realizations. So it isn't the sunshine that's driving this, it's got to be the winds. But I heard you mention two wind things. One is this eddy killing, which I suppose is just wind speed times drag coefficient, makes the ocean currents feel more drag against the atmosphere. And the other would be that the Yucatan Current itself has a seasonal pulsation, and that might be driven in the Rossby wave catchment that drives its wind stress curl in its seasonal Rossby wave catchment, which would be like the Caribbean Sea wind stress curl. So is it about the driving of the current, or is it about this scraping against the atmosphere due to wind speed, or the eddy killing? Which one's more important, or is there a way to take those apart?
Yeah, that's a great question. I'm going to leave that for future research, but I'll tell you a few things that I know so far. The yearly intensification of a western boundary current doesn't only happen in the Yucatan Current. In fact, the way all this got started is because we noticed that the Guyana Current and the Brazil Current follow a similar seasonal pattern. I do think it's likely related to wind. For example, I didn't show it here, but the transfer from mean wind to mean kinetic energy follows a very similar seasonal cycle, and there's also a causal relation from that to mean kinetic energy that we detected. But I wanted to focus on just this mechanism and leave that for future research. That's a great question, great topic for future research. Yeah.
Igor.
Very interesting talk. Thank you. I have a question. So relative vorticity is not a conserved property, so it can be locally produced or destroyed. So are you sure that we are looking at the true barrier, or it's rather front that is produced by local forcing? Or is there any important distinction between the two?
Yeah, so future, I do believe that we're looking at the real thing here. Now, future research is probably a logical next step is to look at potential vorticity, and perhaps that can answer the question that you're posing. But the benefit of doing it this way is that we're simplifying it to the most basic variables, right? We're looking at the most simplified model for this. And we want to see that generation of vorticity, right? That's the, yeah.
Thank you.
Yeah.
And John, I think. Oh, who was first? I'm closer to you.
Sorry, John. Two comments. So one related to Igor. You gave a very long list of reference. I think the first one, but the first person read very early work, and it was actually based on potential vorticity, and I think that's something that was not measured. Anyway, so. And the other thing is that here in the group of Billy Colaflo, a couple of years ago, I will not remember the last name, but Nectaria and Jan, a postdoc, they did a lot of work. I did actually collaborate in some of the papers. And what they found was also something that you didn't mention, and it was transport from, vorticity transport from the Caribbean through the Caribbean eddies. And some of them stay blocking the Yucatan channel, and that was part of the mechanism to make the loop current actually get mature. But I mean, I don't, maybe it's related.
Yes, thank you. So, yes. Now, the beauty of this mechanism is that it's not where exactly these cyclonic perturbations are formed doesn't matter. If they come from the Caribbean, then they're still going to be intensified in the same region. So the mechanism still holds. That's one thing. Now, where exactly these eddies come from is a bit open. It's still being debated. In my view, there is surely evidence that they do come from the Caribbean. We know that much. But at the same time, modeling and observational studies using what do you call these? The profile observations. Okay. Huh? So gliders. Sorry. They've reported that loop current frontal eddies are formed within the Gulf of Mexico. But it seems perhaps this paper here under review, Ranela 2025, they offer perhaps a reconciling view between these two options. Yes?
Yeah, but I mean the cyclones, yes, but the anticyclones are actually something, the ones that are blocking in the Yucatan are anticyclones as well. Okay. So the transport of vorticity, but anticyclones.
Okay, yeah, I'll need to look into that.
Yeah.
Yeah, and at any rate, this offers a nice nuanced view that sometimes it's one, sometimes the other. So that's a good paper to look into.
Thank you for one of the best talks I've heard in a while. This is a terrific subject. There are often loop-like features that are formed downstream of Cape Hatteras. And some of these are quite large meanders, and they pinch off. There's an example of that given in William Varnach's intro oceanography text of an eddy in the process of pinching off and reattaching and pinching off and reattaching and then finally pinching off. So I'm sure this kind of mechanism goes in probably in that area as well. And then lastly, I think that the process of vorticity in the Mediterranean is probably one of the least studied and perhaps most impactful upstream things. Those eddies, at least the seeds of some of the vorticity is probably brought in from the Caribbean, and the current that runs through the islands is shredded basically. And so you have bits of vorticity somehow coming out of that generator, and then you have a number of ridge structures in the Caribbean which may diminish or stretch the vortices in a certain way, and then the formation of the Yucatan Current within the Caribbean is, to my mind, one of the more interesting things, and maybe you have some of the tools that might actually be necessary to look at that. So thank you for a great talk.
Thank you very much. Appreciate those comments. Yeah, that definitely sounds fruitful.
Okay, I don't see any further questions, so thank you very much again.
Yeah, so I think we will stay for lunch, right?
Yes.
Okay, so if anyone want to join us, we will have lunch here in the campus.
And if someone wants another cookie, we still have a lot of cookies there. Everybody needs to take at least one on the way out.